Hello, I'm Abhinav Rajiv Kumar and I am a third year undergraduate student. I'm an engineering student at SRM Institute of Science and Technology. And today I'll be reading or basically explaining this paper, State Stream Transformer. It's one of my favorite papers of all time. And I'll be talking about this because it's been it's a very fun paper, I feel, because it talks about something and it talks about concepts which I find interesting, and other people would also find interesting. Um, this is not a basic paper, in my opinion. Like, I feel that you should have some prior knowledge before trying to understand and read this paper. So I have a checklist, you could say, or like notes basically of papers which you should read before trying to understand SST. And anytime I say SST, I mean state stream transfer. So obviously, red means papers which you should definitely read before trying to understand SST. This orange sticky note basically means they're optional to read these papers, and the titles are exactly the same. So, like, if you just search them up exactly the same, the first paper which comes up, that's your paper to go to. And then blue is basically like, uh, if you read it, it would be better, but you don't have to explicitly read any, any reasoning or metacognition in AI paper. And when I say that, I mean any, chain of thought prompting based paper or something like that. You don't have to read them, but if you did read them, it would be good. So let's begin. State stream transformer, the title is this, emergent metacognitive behaviors through latent state persistence. So I decided to upload this YouTube video because I want to talk about this paper, obviously. But I'm also like an advocate of knowledge being there to the public. And right now in this video, I'll try to talk about this paper. Mainly its architecture, because I feel the architecture itself over here is very fun. Uh, so in this video, I'll be talking about its architecture and a little bit of like the what the paper is about. And then in the next video, I'll try to implement this paper myself on a simple version of this, uh, but I'll try to do it myself. So this is a 25-page paper. It's a good paper. There are some formulas and mathematical formulas as well, which if you have a good understanding of, well, maths, and you should be able to understand them, but I'll try my best to explain them with this canvas over here. So we'll go aside. If you want, you can take a screenshot or you can just keep them, pause the video or something. But I'll go aside for now and we'll start drawing stuff and everything over here. Yeah, so this is fun. Okay. So the abstract, let's try to understand what the abstract is basically saying. In summary, they are introducing a novel architecture, which means it's a new architecture. So they are trying to address the lack of latent computational continuity, which is not present in current transformer models. So it uses something called sliding window latent state cache. So these are all certain keywords and key terms which I feel should be jotted down. So I'll try to jot them down over here. Let's add a sticky note over here and we'll make its color something like purple. We'll call it as keywords. And first thing is sliding window latent state cache, and it has something called a weighted decay. So this is basically being done to maintain persistent states, that is keeping the same state throughout the whole reasoning process. And so it's able to over here it says that it's able to demonstrate enhanced reasoning and emergent metacognitive behaviors. So we'll try to understand all of this as we go further into it. As if we scroll down to the architecture, there are multiple sub points or subcategories, which you could say. There is the core architecture. basically it's based on top of the Llama architecture. So that's why that was one paper which I said you should read, so that you understand how Llama's architecture actually works. So because it's built on top of it, it basically adds a persistent latent state mechanism to the Llama's transformer decoder. So we will understand that as we go further and further. And then 3.2, which is latent state mechanism, basically it introduces a weighted decay, and it introduces a sliding window which is basically controlled by alpha over here, state stream strength. Basically how much of previous state is existent during the reasoning process, that is calculated via alpha. And then there is the forward pass dynamics, and basically it details like the formula and everything. It talks about how the computational process is actually occurring. So that is the attention and the state cache updates, everything. And then there is a state evolution process. Basically it talks about the recursion per token, so that it can evolve to more states. And then there is the processing cascade over here, which in basic sense it talks about interleaved attention. All these might sound like keywords which are very important, but they're actually pretty easy to understand once we start exploring the paper more. Like once we start talking about the paper more, it will become more easy to understand. So like it describes about interleaved attention and the states which is persistent across all the layers. Then obviously over here is the implementation details, and then 3.7 is the weight configuration. Then fourth is something which I would want to tackle in a further video, but if I have time I'll tackle it in this video itself. The first one is about the observations and the validations. Basically it in this point they talk about unexpected repetition patterns, which was controlled with the help of frozen weights and settings which are predetermined. Then in the second subsection, that is introspection behavior analysis, they talk about introspective responses, that is states which are able to show self-awareness. This is a very key and highlighted point throughout the whole video, because the main aspect of this paper is to improve and work upon the reasoning process itself. Then in 4.3 there is hypothetical reasoning somewhere over here, hypothetical scenarios. So basically they are talking about hypothetical reasonings, that things which require planning or which require strategy, that is highlighted and tackled over here. And then there is the patterns of all these reasons. Famous test of strawberry problem. This is also a very famous problem. Essentially it talks about how many R's there are in strawberry, right? Like over here we can see that it's mentioning there are 2 R's in the word strawberry, whereas the reality is there are 3 R's. It also talks about that as to why that is incorrect and how they have been able to improve this in this implementation itself. Then in the fifth section, sorry, I missed out of this. This is safety guardrail adherence. This is my personal opinion. The way safety guardrails are added to transformers, I feel they could be improved, because we require models which are not uncensored but are able to give expected answers and some unexpected answers, because the main aim of making all these models is to essentially allowing them to think on themselves, think by themselves, reason. Like if we take example of previous years transformer models, they were not able to do any sort of reasoning. Like if we take a visual example, let's go over here, okay, and let's assume I'll just draw. My drawing is not that great, but I'll try my best. Let's assume this is a switchboard, okay, and there are light switches over here, or there are just switches, okay, they are not labeled at all. 2 rows of switches. One is for fans and one is for lights. Now us as humans, we have the capability to check in a room when a light or like when a switch is hit. If this switch is hit, if a light is turning on or if a fan is turning on. O is like light basically, and F is for fan. Now with this we'll be able to link it like this, and our brain will be able to reason and will be able to set an expectation that maybe all three of these will also be related to lights, and if we try it, then that it turns out to be true. And then our brain will just default into like a if else loop, if you could say. If this whole row is lights, then else is that this will all be fans, correct? So our brain is able to do that reasoning. Were previous models able to achieve this type of reasoning? No, because they were not able to think like that. The capability to think is something which is being worked upon extensively. And I have gone a bit astray, but whenever one of my research interests is using explainable AI for building trustworthy ML models. And I believe that the way guardrails are written, attacks or not attacks, it basically stops the model from being from allowing it to think freely. Us as humans, we are allowed to think freely. Some might not have freedom of speech, but we are allowed to think freely, right? A model is not being allowed to do this because of guardrails. So in my personal opinion, we need a better way of writing guardrails which allows model to think freely, but they are still protecting the user from harmful responses. That's also something which I worked upon in my internship, and it's fun to understand. So that is the 4.5 section. Then in fifth section, it basically visualizes the FFN output patterns. It visualizes it with these graphs, and it talks about that. And then there is there are benchmarks, and there is the conceptual framework and all that stuff. So this is basically, if we want to interpret these results, we could do that later on. But our main aim of this is to understand why this paper specifically, right? And to understand that, we need to dive into its architecture itself. Obviously, there is the introduction and there is the background and context, but I feel these can be understood, and they are mainly talking about past papers and what they struggle with. That is essentially reasoning, and how layers play like a crucial role for these attention gated responses and everything. So let's try to understand the architecture itself. So let's take a screenshot of this and we'll add it over here if it supports adding it like that. It does. Let's go. Okay. So let's move this a bit down, and then let's decrease the size of this a little as well. Okay. Okay. So this is the architecture which we screenshotted from the model, from the paper, sorry, from the paper. Let's first note down the big changes which we can see in this implementation itself. Let's take purple color, which I like. The big changes I'll write down, then we will tackle the whole section one by one. Traditional transformers which are there, that is including Llama, they process token independently. So that is, each token is processed independently in terms of their intermediate states. So let's write down things which are different in SST. Okay, so basically what Llama and any other sort of model does is, let's assume we have a token over here. Okay, we are just relating it like this. We have a token over here, and these all these tokens which are generated based on the words which are there, any sort of words which are there, these tokens are being generated. They are processed independently. That is, this token will be processed on its own, this token will be processed on its own, and this token will be processed on its own. And then after these tokens are generated, the model discards the hidden states which are inside that. That is the outputs of attention which is there, or maybe FFN layers, that is feed for forward network layers, or anything like that. And it starts fresh for the next token, and it's relying on something called KV cache. It's relying on something like this. So we will note this word down over here as well, KV cache. To understand sliding window latent state cache, we first need to understand KV cache, right? Okay, so we have noted that down as well. So basically the KV cache, in simple words, it stores the past key and values which are there. So if you can, if you think of a dictionary, any sort of, if you think of a Python dictionary, it's basically a mixture of keys and its values, right? So a KV cache is basically a Python dictionary, but for attention. So that is the keys and values which are there for attention. It stores them in its cache. So what does this allow? This allows autoregressive generation, which removes the need and requirement of recomputing every single thing. Because what do we want? We want the prompts which are written by user to stay in context. That is, it should stay in the memory. We don't want the model to forget what it's talked about and what it's being talked about in the past prompts. If I write a second prompt, it should not forget what I wrote in the first prompt, because people would like to continue their conversation. You don't talk with people with a new topic every single time. Now, you might be wondering that why does persistent state? You will notice that SST does something called persistent state latent state mechanism, which was a keyword which we noted down first. Persistent computational context. You will notice that throughout the whole paper it talks about persistence, which basically allows the model to retain these concepts, that is, retain the computational states which are generated across tokens, and it allows it to evolve it, in the sense that if, let's say, this token is A1, okay, we're visualizing this for now, not with formulas or something like that. We're just visualizing them because visualizing is good. So let's assume this is A1 and this is constant, and this has been discarded, the attention layers and the FFN layers, they have been discarded from this. In SST, it does PLSM, basically persistent state, persistent latent state mechanism. Yeah. So what does it do? Like I mentioned, it allows it to retain and evolve its computational state which is there across the whole of the token generation process. So when it is being generated, it will be able to update it on the go. You can think of it in simplest terms, it's able to update it on the go to A2 or A star or A dash, something. Okay. And why is this powerful? This is powerful because it creates a continuous memory system. It allows a memory state to be continuous during the reasoning process rather than getting reset during the during each step, which is there in old transformer or Llama's architecture. It allows for this continuous memory. Now your question might be, or any person who's reading this paper, they will ask a question that why this? That is, why does persistent state matter? Why is persistent state important? So in standard transformers, the context is limited to what is captured in the KV cache. So whatever is captured, this is static and it's very token specific. Like if this token has certain information, if this token has certain information, it's dependent on this completely, and this is being dependent on this. So if this token is not generated properly, let's say, or if it doesn't have enough information, the thing which is being stored in KV cache will also not be correct. Now this works well for short term, but let's say you are doing for long term reasoning or something which is taking up lot of computational context, for context windows exceeding a certain token amount. Let's say it's exceeding x tokens, and let's take x as like 90,000. Okay, the model might start to hallucinate, and we don't want that. SST, because of this continuous memory system, it allows it to maintain a dynamic and evolving context. Like I mentioned, it allows it to evolve the context, and this will improve the reasoning and the coherence and even metacognitive abilities. By metacognitive abilities, I basically mean the ability for the model to reflect on its own generation process, right? So let's understand how this is being implemented. This is part of the core architecture. Now when you read the text, it's not that visible or that understanding, like you can't understand it that well, so you'd have to go to this diagram. So let's go to the diagram and let's try to understand it one by one. So the keywords which we talked about, let's write it down over here so that we don't forget. We talked about KV cache, we talked about latent state, there's also transformer blocks, there's something called auto-regressive token generation, which in my opinion is self-explanatory, but let's just note it down so that we can tackle it later. Auto-regressive token generation, and then final point was persistent token generation, and let's add an arrow saying continuous memory. So continuous memory. So we will tackle all of these keywords while understanding this section, this whole section architecture. All of these will, each subsection will have certain keywords which will be tackled, which I'll talk about, and we'll move on to the next session only after I have explained majority of these keywords, or complete all of these keywords successfully and nicely. So let's take a very basic or a visual example. So let's try to do something like this. Let's draw a square over here. Okay, now we will divide this square in two parts. One is for traditional transformers and one is for the SST transformers which is there. So we'll visualize the whole aspect, then we will move on to relating that with the diagram which is over here. Let's move the diagram a bit up over here so that it's visible, and let's move this here and let's move this here, and we'll first visualize it over here and then we will talk about it with the diagram itself and tackle all the keywords also. So conceptual overview, I'd like to call this CO, conceptual overview. Let's imagine a traditional transformer as a chef. So there's a chef over here, let's take him as X, we'll take X, so X chef over here, right? So he is cooking dishes, any dish, he's cooking them from scratch, whether he's making paneer butter masala or he's making chicken tikka masala or any sort of foreign dish or anything like that. He's making all of them from scratch. Like even the ingredients themselves he's growing, and he's growing them on his farm and he's making them from scratch. So he's able to make them from scratch. How? He's able to make them from scratch by referring to a list which is over there. These lists might contain instructions. I'll write over here instructions which basically talk about any previously served dishes or any previously cooked foods, which is the KV cache over here. So we link this instructions of past food items. So instructions of past food items is basically our KV cache. So hopefully we understand KV cache much better now. Now the SST chef, however, so let's go to SST over here. The SST chef, he keeps a pot or a dish or whatever, he keeps it on a gas stove and he is keeping it simmering, in the sense that he's keeping it evaporated, he's keeping it hot, and he keeps adjusting the stove's temperature. So instead of a circle, let's do okay, let's just do it with this temperature. Okay, let's just take dot, okay, dot C. He's increasing them or he's decreasing them based on the new dish while blending the flavors from the past. So let's say you are making rajma masala or something like that, and he already had gravy of, let's say, chole masala present already. He can use the understanding or maybe the chole masala itself for rajma masala. It might not taste as well because we're trying to visualize it, but that's how the SST transformer is doing. So it's blending the flavors from the past while adjusting it for the new dish. So new dish keeping in context of the past dish, if we take it like this. So new dish is directly dependent or not directly dependent, it is keeping the context of the past dish. This persistence which is over here, this whole process of remembering the past items and adjusting them dynamically on the go is what we are calling persistence. So we have tackled persistence token generation, that is what persistence basically means, which is continuous memory, and we have tackled KV cache. There is also latent state, which we'll talk about. So this let's first talk about this persistence. This persistence is what is allowing the SST model to think across tokens. Like I mentioned, the keyword is think. So this is what it's allowing the model to think across tokens, and it is also allowing it to reason complex problems or essentially maintain a train of thought instead of a chain of thought. It's now maintaining a train of thought which is going continuously and evolving at a rapid state, let's say, because it's able to keep them in memory much more efficiently. And this persistence is something which occurs in SST, but it doesn't occur in traditional transformers because its architecture is not built like that. So because this persistence is not there, this graph also will not be achieved in the sense that this train of thought which is being done in a SST transformer model, it's not there in a standard transformer model. So this is built on top of Llama's architecture over here, while adding a layer of continuity which allows it to maintain memory much better. So we have understood KV cache. Let me take a different color. We have understood KV cache, and we have understood persistent token generation. Now, so basically, if you have a understanding of like neural networks, you know that latent state, or they're sometimes called hidden state, basically. It basically is a numerical representation, you can say. It's something which is internally happening in the network, and it's a numerical representation, so represented by numbers of the information inside the network. So it's like the set of values which a network uses to store, or sometimes it even uses it to process information as it performs a task. You can maybe think of it like working memory, or something which another easy word which you can think of is your inner thoughts, essentially inner thought process at that specific point in time. It's called latent itself because it's not observable, in the sense that it can't be observed from outside because it's happening inside the network's computation. And if we talk about it in the context of transformers, latent state is essentially a vector. As much as I know, it's a vector which is a one-dimensional array, or sometimes it's even a tensor, which is a multi-dimensional array of I believe it's floating point numbers. It's a array. It's a vector or a tensor of floating point numbers, and the size of this vector or tensor is what is called hidden dimension, which is denoted as D in this paper. It's somewhere over here. Okay, there are a lot of D's. I didn't think that through. It's somewhere over here. I think we will get to that. Oh yeah, here it is. It's D over here. D is the hidden dimension, like it mentioned. So, for example, if we go back to this architecture, if we check out Llama 3.1, it's 8 billion parameters model. It has a hidden dimension of 4096. So it basically means that each latent state which is there is a vector of 4096 numbers. Now it also mentions something about FNN output over here. So what do we get or understand by FNN outputs? Over here it mentions feed forward network. So in both SST and standard transformers which is there, the latent state which is mentioned over here, which I mentioned over here, is specifically referred to the output which is generated by the feed forward network within each transformer layer. Correct. So what this FNN does is it applies a non-linear transformation. So it applies that to the data, and it's able to represent the output a higher level, and it's a more abstract representation of the input, if you can understand. So if I were to explain it much simpler, latent state basically is it's essentially capturing the model's understanding of any input which is there, any input sentence which is there up to a particular point, like the sequence of it. This understanding is encoded with a numerical value. Let's take a numerical value of a latent state vector. It's not a, you can't call it a conscious understanding, but it's more of a complex set of relation between learned relationships between like words and concepts which are there. You can represent latent state with dimensionality reduction if you want. Now so we can we're assuming that we have understood latent state as well. Now final is autoregressive token generation. What does autoregressive generation mean? It means that it's generating text one token at a time, and where each of these tokens are completely dependent on the previously generated tokens. So past tokens, let's take past tokens which are there. This is how most of the language models, which is both SST and standard transformers, that's how they produce text. Now let's go even deeper. Let's go even more basic. What is a token? Token is a basic unit of text which is processed by the model, right? It can be word, it can be a character, whatever. It depends on the model's tokenizer which is there. Then it goes through a probabilistic process. It doesn't just choose what a next token could be. Like if in the sense that it can't just predict what the next word can be. And there's a beautiful explanation and like a visual explanation of how transformers work visually. Let me see if I can find it. How do transformers work visually? I don't know if this is it. Okay. This is a very advanced, you could say. If you wanted a much simpler one, there is another one. I can't find it right now, so if I find it, I'll put it in the description of this video. But like I was saying, it's a probability. It assigns a probability to each possible token in its vocabulary. Now we know that after A comes B, but a model doesn't know that. It can maybe give C, it can maybe give D. All of these will be given a state of probability 0 0.1, 0 0.01, 0 0.02, you can say something like that. Okay, so uh, the next token which is there is sampled from this probability distribution which we have. There is greedy decoding and there is other sampling methods which are there. So let's take an example from the prompts which are over here themselves. Okay, not here. Okay, yeah. Here's one. That's a G mode, a good one. Or this one. Why did the coffee bean go to the doctor? So, uh, sorry, this is the output. That's my bad. Let me just think of a prompt. Let's just write a prompt over here. That was my bad. I didn't realize that was the output. I thought that was a prompt. Let's ask what is the capital of India. The capital of India, question mark. Okay, we're asking this to a model. So the model will predict India as a high priority. Like let's give it a 0.8 rating. Okay, India has a high priority, and it adds it to the sequence. So the capital of India is New Delhi, right? So the output will come like that. The capital of India is New Delhi, or the capital. Let's take another country. Let's take France. If it's France, then it knows that it's Paris, right? It's the same concept which is happening over here. So uh, that's how autoregressive generation essentially works. So we have understood all these keywords now. 2, 3, 4, and 5. We are assuming that we have understood them now. So let's move on. This was the core architecture. So let's move on to a bit of maths, which I love. If we were to explain all of this mathematically, even if it's the things which we know, how would we do it? That's the question. So uh, we will try to understand how this is being computed mathematically, and if it's, if we are successful in understanding it, then it's great, and if we're not, then that's a different story. We'll have to think about that later on. So if you want to represent, all of these states mathematically, we first have to understand the basic components which are there of um, the base model which is there. That is the Llama transformer decoder, right? So it has two things, like the two main components which are there is the multi-head self-attention mechanism which is there, and there is the FFN, which is, I'll write the full form here, feed forward networks. So now we have a understanding of what feed forward networks are and multi-head self-attention mechanism is, assuming that you have read the Llama paper. If you have not, then my advice would be to read it. But basically, if I were to explain it very simply, multi-head self-attention mechanism, it allows the model to give importance to different tokens during the input sequence via a formula. We'll link these formulas now. So via a formula, my handwriting is not that great when I try to write it, so we'll write with text, and the ones which require me to convert to pen, I'll write with it. So there are three different variables, Q, K, and V, which is there. So Q is for queries, K is for keys, and V is for values. So this is it computes all of this from the input, and it applies attention score and aggregates, that is it basically shows the explanation or shows the information across the sequence. So this weight giving Importance of weight giving, importance slash weight giving to different tokens is done during the input sequence, right? So attention QKV is equal to, we use a softmax function, and I assume softmax function is known to people, but it's basically an activation function. It's also, I think it's known as soft argument max or something. Basically, it converts a vector of real numbers into a probability distribution. If you want a very simple explanation, it does that. There are real numbers, a vector of real numbers, and it converts them into a probability distribution which is there. If we were to graph it out, it would look. Oops, I changed the color of this, but that's fine. If we were to graph it out, it would look something like this. Okay, that's not the greatest diagram. Something like this. It's basically like a S, you can say. Obviously, I've ran out of space over here, but it's something like this. Okay. So, we've understand all this now. So, where was I? I was on softmax, right? So let's go on that. So softmax, and it's it basically applies the function on that, right? So it's softmax of the queries and the keys which is there, and q is raised to the power of t, and then there is the square root of dk. Dk over here is basically the dimension of the keys which is over there, and there is v which is for values. Now this is the formula for multi-head self-attention mechanism, which is also there in the Llama paper as well. I just wrote it so that if people wanted to understand, or if people wanted to know it again, it's over here. So importance of weights, different tokens via this formula, done. Now next is feed-forward networks, right? So what do we understand by feed-forward networks? Basically, it's a fully connected neural network, you can say, and this neural network is applied independently, like I mentioned, to each token's representation. So it's usually between two linear layers, and it has a non-linear activation function like GELU, you can say. I like to call it GELU. So formula for this would be let's just it's this independent token. Independent. It's just basically independent token representation. Basically, the neural network is applied independently to each token's representation. The function would be something like ffn, let's take, of x with the activation non-linear activation function. So GELU, and we'd have the weights which are there, b1x plus b1, and I think as far as I remember, it's w2 plus b2. Basically, what this does is it enhances the model's capacity to understand any sort of complex patterns which are there, and it's able to capture it with this layer. Now, the original transformer which was there, it only had an encoder and a decoder for tasks like translation, whereas Llama and SST both, they use decoder, and this uses the autoregressive generation function which we talked about before. It does it with a causal attention mask. So basically it prevents it from attending to future tokens so that it can't cheat. Essentially, it should not be able to guess, or it should not be able to see what is the next word or token in line. So the key properties which are there in SST, which is there in Llama also, that is the positional encoding, which is rope, that is rotationary position embeddings, and it also has normalization, which is root mean square layers normalization. If you want the formula for that, I believe it's something like, if I type RMS n of x, it's something like x by, it's a square root of something. I don't remember it right now, but I'm pretty sure it's mentioned there in the Llama paper. So we have talked about the difference between SST and Llama. We've also talked about the similarities which is there. So if we were to, let's say, tabulate them, how would we tabulate them? Let's do a table. Let's draw a big table over here. Let's bring this down a little, and let's change the color, and let's draw a line between them to differentiate between a standard transformer and a SST transformer. We already took a visual example of it, but let's write it down in text also, because we like text as well. People like to see text. So SST over here. So how does a typical transformer handle state? So our first point will be related to state handling. How is it handling state handling? So in traditional transformers, it discards them, right? It discards them immediately. It discards the states after each token. In SST, it keeps them for persistent latent states across tokens. So it keeps them basically. If you want to keep it in simple terms, we'll do keep them. Then next is context. That is a key point which we should tackle. Context. In the traditional transformer, it depends solely on the KV cache. Depends on KV cache for past context. Correct. It depends on KV cache for the past context. Whereas for SST, it uses the KV cache, and it also has its evolving latent state cache, which I mentioned is just it's updating it. You can say, if you want to keep it in simple terms, it's updating it. Then there is computation. Then there is, if you want to talk about purpose, like I've jotted down notes for this, which I'll make public later on after the video is uploaded. I've talked about all of this, but I don't have a script, so I have to think of the script on the go while reading out these notes. So I wanted to be a bit more visual, because I have just written down text notes and they're just understandings of what I have. So this was the core architecture. So we were able to visualize it over here with this pot example. If you wanted a visual example, the pot example is over here. This is the architecture, which is very similar to Llama's state. It has a normalizing function and linear layer and softmax function and everything. The latent state cache, this is the new thing over here. Feed forward and latent state caching and the normalization. We'll discuss all of this later. I feel that the way I'm explaining things is a bit rough, but if we are able to understand it, then I think we are good. So let's move on to another empty part of the campus, and let's zoom in over there. Okay. So next step of the paper is, let's scroll up. It is latent state cache mechanism. I keep mentioning this latent state cache mechanism, and you can see that they have written very few things about this. Like, they've not gone into deep, but we have to go into deep to understand how it operates at the block level, that is the transformer block level, how it is operating at that. So essentially, the latent state cache which is there, it's the heart of it. If you had to put a word on it, it's the heart. I'll draw a heart over here. The latent state cache, LSC I'll call it. Latent state cache is the heart of the whole SST's, that is the ability to be able to maintain the persistent memory and computation across the tokens. That is, LSC is helping for that. Now this operates at the block level, like I mentioned. That is, each layer of the SST which is there, including the including the attention and the feed forward networks which is there, all of them have their own independent caching system which evolves over time, and that's what's allowing this to maintain that memory. So like we mentioned, traditional transformers, they discard their states after each token is generated, whereas SST allows it to blend. There is this blend of past token, blend of past token with the new token which is about to be generated. So it creates a stream. If you want to think of this, it creates a stream, a river. It creates a river, you can say, of the memory. So what is it basically doing? Let's see over here. So according to this text, it basically means that after the attention mechanism processes an output over here, after the attention mechanism is processing an input, sorry, the latent state cache, which is over here, it's blending the result, that is the hidden state, with a cached version of the previous state. This blending is controlled by something called weighted decay sliding window. So that for this second section, that is our keyword. Here's a sticky note. We'll make it purple again. Keywords for 3.2 section. This is so weighted decay sliding window. I realized that I mentioned this, I believe, in the past one as well, which I feel I should remove now. Let me remove this. Now the ticks are messed up, but that's fine. It's okay. Let's move on here. Okay. So weighted decay sliding window. We'll tackle this word later, but this is basically being affected by this parameter over here, that is alpha, that is the state stream strength. Like I mentioned, it's how much the previous state is existent essentially. So that specific parameter is dictating how much influence the past has on the present, if you want to think of it like that. Now, why does this matter? Like I mentioned, majority of the questions which we need to ask is why. This is a novel method, right? But why do we need this? What is so special about it? What is so special about it which we don't have right now? So, like in standard transformers, there is Llama. And we were taking Llama because that's the architecture which is built upon. The only sort of persistence which you can think about is coming from the key value cache, that is KV cache. It's coming from there. Now, they are reset, right? That's the hidden states which is there. That is the outputs of the attention or the FFN layers or whatever. They are immediately discarded and they're reset for each token, which, like I mentioned, it limits the model's ability to keep a continuous computational context. So the transformer block layer, the block level, so it has the simple multi-head self-attention, it has the FFN, and it has the residual connections and the normalization and everything. Okay, so that's for the transformer block level. Then there is the input tensor, which is represented by this formula over here. Now I don't want to write this, so I'll take a screenshot of this. Work smart, not hard. I mean, work hard and smart both, but yeah. So let's tackle this one by one. Right. So this B over here, you might be wondering what this B means. This B means batch size. Batch size. This B means batch size. And what do we mean by batch size? That is the number of sequences which can be processed at the same time. So it's usually one for like a single generation, and it can be more for multiple generations. Now, what is S over here? S is sequence length. Sequence length. sequence length. So what does sequence length mean? That is, it's the number of tokens in the current context. So this thing, this grows during autoregressive generation, and then D, which we know already from the previous section, this is the hidden dimension. Hidden dimension. Like the 4096, which Llama 3.18 billion parameter has. So this tensor, this whole tensor is the input to each transformer block, and it's carrying the token embeddings and the positional information. Now the first step in the block, so let's think of this methodologically, right? The first step in the block is producing a hidden state. Let's take the hidden state as H. Hidden state as H. Very creative, I know, but yeah. And this is based on self-attention. So this is based on, so we'll take it as H like this, and this is based on self-attention. In Llama and in SST, we use group query attention, which you can see over here. Group query attention with rotational position embedding, rotatory position embedding. Sorry. So group query attention, what does it mean? It's basically it's a type of multi-head attention which is specifically optimized for it's basically optimized for it to become very efficient, and it has a causal mask to ensure that autoregressive behavior, that is no peeking into the future, is present. Then there is the state blending process. So we have the hidden state, that is the self-attention layer, that is the group query action. We'll take that as, we'll put a semicolon over here, GQA. This is known things. Second is state blending process. State blending process. So what does state blending process means? State blending process, this occurs during post attention. So if we go back to the diagram over here, this is happening after the attention is done. So after the attention mechanism outputs H, the latent state cache which is there, which is set up, it blends into this fresh state while keeping the context of the previous cached state. Correct. So basically this blending, you can say, is like, mixing of colors. I'll take a visual example also later on. You can take this as mixture of colors. Now the next thing is weighted decay sliding window, and this is a key term which I have targeted for this section, and we'll finally explain it now. What does it mean? Weighted decay sliding window. This is the keyword for this section, which I specifically have highlighted because even I had to go back and read some papers and understand it both methodically and like mathematically and everything. So the core idea, let's talk about the core idea behind it. So the core idea is to combine the current information which is there. Let's take a different color. Let's take dark green. Okay. The current information which is there, that is the output of the attention mechanism, which is denoted as H in the paper. It's denoted as H in the paper. Yeah, over here, attention computation. It's denoted as H. So basically, the aim of this is to combine the current information and the memory of the past, which is denoted by CT minus 1. So state cache blending, post attention computation, state cache blending. Then we have the feed forward processing and cache update. CT is equal to out. Understood. So this weighted decay sliding window, which is the keyword, is the mechanism which controls how this combination happens. If you want to take like a worded example, it's basically we are considering the past. So consider the past, okay, but we are giving more importance, which means more weight. So, but a but will be there. But more weight will be given to the recent past, and the influence which the distant past has, like something which is like, starting of the context window, that will gradually fade away. So, influence of old stuff basically will fade away. If you wanted a worded example for weighted decay sliding window, we are considering the past, but we are giving more importance to the recent past instead of the old stuff which is there. Because if you think about it, let's take a logical explanation. If you think about any sort of prompts which you write to a language model, sometimes you will notice that your ideas might not link properly, or you would realize that you want to talk about something else. So sometimes you will not just create a new conversation, you will just continue in that specific chat. So if it's still remembering something which you talked about 5 prompts ago, which is no longer needed for your current questions, it should forget about it, right? And that's what this weighted decay sliding window is talking about. So let's dissect this term, like, one by one. So there is the window, there is the weight or weighted, there is the sliding, then there is the decay, right? So the window over here, we're going to go proper deep into this. No, we're going to go proper deep into this. This whole term, we're going to go deep. So window, I'll type it as win. Okay. This basically is, you can think of it like, it's not looking at all the past states which are there equally. It's focusing on the most recent past. So the most recent substate. So x of n substate, subset. So, like we mentioned, SST doesn't have a fixed window size, right? It's a variable. So this effect is similar to a window because of the decay which is there, which happens. It's denoted by y. The decay which is happening. This is dynamic. Then there is the sliding. Basically, this means that the window is moving forward in time as the model processes each token. So let's take 4 tokens over here. For each token generation, the window W is moving forward along with the token generation, because we want a continuous flow of memory, right? So it's moving forward every single time. As each new token is processed, the window shifts, and it takes in the new information which is there, and it removes or it forgets the old information. Or let's be more accurate, like I mentioned over here, it reduces the influence of it. Then there is weighted. This means that different parts, so different time where the window is, they have different importance. They have different level of importance. So the most recent state, that is this state, will have a higher weighting. Let's take 0.8. Whereas this this token will have a weighting of 0.4. Now this might not seem like a lot of difference, but it is huge. Let's be honest, it is huge. The most recent state which is there have the highest weight, and they decrease as we go further back in time. Then there is the decay, which we talked about, which is the influence of the past states, which is degrading over time. So the alpha parameter, which is mentioned over here, is explained more detailfully in section 3.3. So we'll discuss this now. Okay, so section 3.3, forward pass dynamics. Before we go on to that, let's go back to our previous section. So the weighted decay sliding window has been explained, and we will put a check mark on this now. So the keyword for 3.2 which we had has now been explained successfully, and this is how the canvas is looking right now. Let's bring this guy a bit closer so that we know. So this is for whole of section 1, 3.1. This is for 3.2. Now let's go here and understand 3.3. let me just remove this. That's a bit of not doodling. I mean, it was a reasonable explanation, but I mean, it was understood. Yeah. Okay. So, 3.3 forward pass dynamics. It has a lot of formula, and it's a pain to write them in pure text. Like this can be written, but still, I'll just screenshot all of them and paste it in the canvas, and we'll tackle them all one by one. I think that would be fair, and that would be easier for me to do and easier to follow as well. So the first one, that is attention computation, right? So we mentioned alpha. We kept mentioning the alpha parameter which is there, and we can see that in the second formula also. So first, let's go back to understanding what that alpha parameter was basically doing, right? That was the state stream strength, that is controlling how much of the previous state persists. So basically you can it is the control that, of the trade-offs according to this formula, that is the blending state. It's controlling the, it's a scalar essentially, it's a scalar between 0 and 1, and it's controlling the trade-off between the fresh weights which is there and the weights of the normalized cascades, which is alpha, right? So let's take let's say if alpha was 0.027, right? 0.27. So 2.7%, it's an optimal value from the experiments. And then 97, yeah, that's the minus 97.3% is the blend coming from the new state, and 2.7 is the past state. Let me write this 2 a bit better. 2 is the past state, and 97.3 is coming from the blended new state. So let's write it as B of new, right? So this is coming from the blended new state. But even before we move on to that, we first need to understand the whole. We need to understand it visually, right? So let's take this formula itself. Over here, we'll draw a table, and we'll choose a different color for this, and we'll start drawing because we love drawing. So H over here, which is there, H over here in the formula which is there, you can think of it as a splash of paint. Okay, let's take it as a splash of paint. Over here, this is a canvas which we have, and paint has been rushed on it. Okay, that is the splash of paint for the current token which is there. So token A, right? And then we have this C of t minus 1. So C of t minus 1, what does that mean? It's basically the you can think of it as palette of colors which have been used in the past. So they are there in the canvas itself. So like a bit of green is there, and a bit of orange is there, right? So these are present, but they're slightly faded. You can see that blue is overpowering them because it's more abundant, right? And then the alpha, which is over here, alpha, that is basically determining how much of the fadedness is blending into the fresh splash which is there, which is of blue, which is creating a new shade completely, which is your H blend. Okay, so this, if you were to understand visually, this is how you would understand it visually. So let's say it chooses that this orange is more important, and it might do multiple of it. So like this. Now these blends are there. Now blue and orange have blended in nicely, and green is still there, but it has blended out a lot. Okay, so this is for the second formula. Now for the first formula, this formula which is there, H is equal to x plus attention, and it's the normalizing function of x, SP. There is the starting position, then there is the rope embedding function, and there is the attention mask matrix, right? So we know the attention mask matrix function, which is already there. I had written it somewhere over here. which is a 1 by actually I didn't write it, something like this. So it's basically um, yeah, okay, sorry, I jotted down my notes a little bit wrong, so that was my fault. Anyway, over here, so x, so what does x represent over here? This is the input tensor which we are getting, right? This is the input tensor which we are getting, input tensor. So the shape of this is BSD, buzzard, I like to say buzzard. So like we know, B is the batch size, S is the sequence length, D is the dimension. Okay, so X is usually over here, X is usually the previous output or the output of the previous block, which is carrying the current token representation. So output of the previous block which is there, but in the current token representation, right? So that is your X. Then we have the root mean square normalizing function, which is inputted before attention. So this stabilizes the input by normalizing the magnitude, I believe. Yeah, it normalizes it, and it's a standard practice in Llama, which was done as well. So this is not new. This one is not specifically new. The new part is this. These two parts are the new part. This is still same as Llama, which is there. SP is the starting position, so it's an integer which basically tells you what the position of the current token is. So if it is 5, then that means it's processing the 5th token which is there, right? So that's SP, and it's usually used for applying positional information and the causal mask attention matrix. So that's why SP is required for the next two pointers which are there. So rope, which we know, it's used to encode the token positions into the attention mechanism. The formula for that is something, I think it's Q dash is equal to Q into E of iota theta m, something like this. I don't remember it that well. And then there is K also, which is there. K dash is equal to, it's something like this, something similar to this. Basically m over here is the token position which is there, and theta is like the frequency parameter which is tied to D, which is your hidden dimension, right? So we have cleared that out. Now we have the attention mask matrix, and this basically computes the group query attention which we have, that is the multi-head self-attention matrix. Right, this is used in Llama as well, and the formula I had written it in the past, so it's the same formula for that. So this all is done. Then there is the residual context, if we have any, via the plus X. Basically, it adds the input X back to the attention output. It's a standard transformer practice. So H is equal to X plus attention dot, and dot is the whole formula. Right, H is the fresh hidden state which we get. Now we then do the cache blending, which I explained over here. Basically, H is the attention output which we received from step 1. So this is over here. Then there is one. Then there is a C of t minus 1. So like I mentioned over here, it's the previous cache state. So caches which were I'll just write it like that, previous cached state. So basically it stores the last token's forward pass which is there, right? So the shape of this is B, S and S minus 1 and then D, but it's aligned to S, right? And then this part is the persistent memory of the prior any computing which has happened prior to this layer. And then there is the RMS normalization function on this, right? And then there is a slice operation. You'll notice that there is a slicing operation which is happening over here. Let's put an arrow to that. So what is this slice operation doing? It's aligned to t minus 1, right? It's aligned to the previous cache state. So basically the CT minus 1, it was computed for S minus 1, right? this would involve something like padding the zeros for new token, or essentially you're selecting the last relevant state which is present and you're extending it. So what this slice operation is doing is ensuring that c of uh, c of t minus 1, which is there, is matching the shape of h. H's shape is being matched by c of t minus 1. This is that's what that slicing algorithm is doing, and you can see it over here. The slice ensures alignment with its current sequence length. Then we have the third equation, which is feed forward processing and cache update. Right. So we understood the first equation now, and we have understood the second equation. Now we have to understand the third equation, which is also pretty important, because we are using the H blend from the previous output, right? So we are calculating the output now. So the blended state which is there from step 2, we are using this for further processing. Now we have the normalizing function on H blend itself. So we are normalizing that. And then we have the feed forward network layer, which is the simple two, you can use the W1, W2, the formula which I had mentioned before, and GELU and everything like that. So there, it's basically doing a residual connection between the FNN and the H blend. So basically output from this FNN whole function, it adds it to the H blend with this plus, and that is being that is producing out with the shape BSD, right? We have to ensure that the whole shape of this function of this whole equation is equal to that state, and then it updates the latent state cache which is there with the final output of the forward pass. So CT now becomes CT minus 1 for the next token to ensure that the persistence is there. So if we think about this step by step, there is the attention, right? Attention computation, where it is processing X with the context from KV cache, which is producing H, right? Then we are blending it. So we are merging the H with the cache state, that is CT minus 1, using alpha. So the alpha which is there, and which is resulting in H blend. Right, and then we have the FFN, which is finally doing the feed forward processing and the cache updating. So we use the H blend which we received from the second step, and we transform it through the FFN, and we add a residual connection, and it updates the cache with the output, which is over here. This is the out, and then for the next token generation, this CT becomes CT minus 1, and this whole auto-regressive thing is done. So as I mentioned, during generation, SST will process one token at a time. So the KV cache which we have, it will grow with each token, and the latent state cache which we have, that will also grow alongside, because it's blending the past and the present, right, at every single step. So to conclude this whole section which we had, let's again do the diagram. Let's again do the difference which we have been doing for the past two sections as well. We are comparing Llama with this SST because we're trying to understand SST as to why we should use SST instead of typical Llama transformers, right? So that should be mentioned. So SST. Now, the attention is exactly the same. So the first attention is same for both. The equation is same. Post attention, what we are doing. So post attention which we have for Llama, we are it's direct to FFN. If we have H, it's directly to FFN. Whereas in SST, let's write same over here. Okay, that's not a great same. Yeah. And for SST, we are blending it with the cache. So we are getting a H blend, which I mentioned. Great. H blend. It's very hard to write with a mouse, but okay. Then there is the FFN. For Llama, that is the output, that is H plus FFN, which we have over here, right? And then Whereas for SST, it's the H blend plus FFN. Then the state update, which is something which we are tackling, the most important part of this, that is the states. This discards it, right? It is discarded, it's gone into a trash can. Whereas this is updating the cache. CT is equal to out. And then this becomes CT minus 1 for the next token generation. So, why is this important? Because the blending step is ensuring, the blending step over here, which we have, the blending step over here, it's ensuring that whatever, like the computation of each token is carrying a trace of its previous states, which is being controlled by alpha, right? So what does this do? This improves coherence and reasoning over long sequences. If we are having long conversations, it's able to keep context. Then there is obviously stability because of the multiple RMS norms present, right, to prevent a numerical instability, and flexibility. That is the alpha over here. The alpha is very key because that's how it's that's the main part of this whole architecture, which is essentially telling the model how persistent it should be, and it's adaptive. That is, it's more persistent for reasoning tasks, less persistent for something simple like what is 2 plus 2, right? So if we were to visualize this, we would take something like I mentioned, a river. So H is the fresh water. H is water body. It's a river which it's flowing from let's say a dam. This dam is our attention, right? Then CT minus 1, which we have. CT minus 1, which we have. That is basically the river's existing current, you could say. So like let's say CT minus 1 is like I mentioned, it's the existing current. So it will have minerals, it will have sediments of the past, like where it has been in the past, like upstream, downstream, wherever it is going. It will have some sediments, right? Not sentiments, sediments. That is your CT minus 1. Then alpha function which we have is how much of these sediments are mixing together. That is being controlled by alpha. So this alpha function is resulting in a H blend, which means a river body which is a mixture of these sediments. And then FFN. What is FFN doing? FFN is basically refining this mixture, and this new state of river with some minerals present is put out. That is the output, and becomes the upstream memory for the next token. And then if there are more sediments, if they want to be mixed, that is controlled by the alpha, and that is worked upon later. So this concludes the section 3.3. Now we move on to section 3.4. This is a important token. This is an important section as well. So let's tackle this also step by step. There might be a lot of cuts in the video because I have to take breaks, water break, or refer to my notes and all that. So it might be a bit choppy, but hopefully the transitions are smoother enough. So yeah, 3.4 state evolution process. This is it, right? Okay. So the core concept over here is recursion per token. So what does that mean? Right, so that's our key property. So let's this is our canvas now. Okay, so let's move down here. Okay, and we'll zoom in. Yeah, okay. So for the last section we didn't have a keyword because it was mainly formulas, but for now we have a keyword, right? Recursion per token, that's one keyword. Recursion per token. Yeah, okay. So in this section which we have, basically it's describing how SST over here, it iteratively refines its latent states which are there within each transformer block, right? Within each transformer block, how is it updating the tokens essentially for a single token during autoregressive generation? How is it refining the states. In normal transformers, it performs, what does it do? It performs a um, single forward pass per token. Now SST introduces recursion into this, right? Recursion is what is helping over here. That is multiple forward passes or iterations that evolves the hidden state before moving to the next token, right? Over here we can see, while this describes the evolution within a single layer, the interaction of these evolving states across a layer creates a more complex dynamic, right? So basically what does this process do? It's using the latent state cache which we have, CT, and it's using that to enhance the reasoning and coherence of a model. So let's try to understand recursion per token. What does it mean? Let's take green. Yeah, recursion per token. What does it mean? In a standard transformer, like whenever each token is there, it triggers one forward pass through all the blocks, that is through all the transformer blocks which is there, and it produces an output that is used to predict the next token. And then these states are discarded, and we all know that. In SST, for each token which is there, the forward pass, which was defined in section 3.3 over here, the forward pass, right, is repeated R times. So over here we can see that this process iterates R times, where R is the recursion count. This can be 2, this can be 4, anything, right? And this is within each block itself. This is within each block. So what is it allowing? It's allowing the latent state to basically evolve, basically improve itself. For each iteration it goes through, it's able to improve itself. So it's refining the representation before giving us the final token output. You could think that this is like a endless self loop, but it knows when to end because we have a recursion like a counter set, right? And why is this done? The paper basically says that a single pass, that is a single pass which is through, let's take we have a single token over here, a single pass through the attention layer is not enough to basically solve complex reasoning which are there, or any sort of dependencies which are there. It's not able to reason. What does recursion do? It basically mimes the thinking process which our human brain has. How does our brain think? It thinks of let's take any topic, for example. Let's topic is the Cars movie, right? Now we are asked to think about the Cars movie. Even before we start thinking about the movie itself, we'll think about Lightning McQueen because he's the main character, right? So our brain goes, who is the MC? It is Lightning McQueen. Lightning McQueen Kachow. Right. Now this Kachow, what is it? It's his key phrase, or it's like his tagline, or like something which he says, basically. Right. So our brain has this thinking process built into us, but a model does not have that. This recursion basically allows it to do that. So it received a topic, right? Let's take blue color now. It received a topic and it thinks about that topic. The topic is Cars movie. Now it gives itself a question. Who is the MC? It says Lightning McQueen. Lightning McQueen. And let's say inside here only it's thinking what could it be, what is his key phrase or tagline, basically over here, the tagline which it has. And over here we are getting a recursion Kachow, right? And he might, the model might think, in Cars movie, is there another MC? Right. Which Cars movie? Right. If it's 2, it focuses more on Mater. Right. So over here, it might perform another recursion, asking itself which Cars movie is it talking about, and then based on that, which MC. Right. Lightning McQueen is still the main character, but the movie focuses on Mater more. So should the answer include Mater? Or should the answer include McQueen? Does he have a tagline? That's another recursion, right? So think of R basically over here, which is there, the parameter. That's the recursion steps or the recursion count, you could say. So this thinking process which the paper talks about, basically it allows the model to refine its understanding. That is, it allows to improve the understanding of the token which it currently has running, uh, and uh, and it basically thinks, or it connects it to the blended or the persistent states which are there, in the past. It connects them basically, and this ties a little into the metacognitive behaviors which is there in us humans, that is self-correction, right? If we are making a mistake, if we are stuttering like this, our brain performs self-correction. So this recursion also helps in self-correction, which is a um, metacognitive behavior, and this recursion also gives it time to adjust its internal state, right? So lots of things are being achieved with this recursion. So the key parameter which is over here is R, right? That's R. So that's basically the recursion count. That is how many times that specific block's computation is being done, essentially, you could say. So like if you take R is equal to 2, which was used in its phase 1 testing, somewhere over here, 1 second, R is equal to 2, okay, great. Maybe I wrote down the notes a bit wrong, but basically let's take R is equal to 2. That can be used in initial states, and then R is equal to 4, that can be used for other further benchmarks, right? So we understand what we mean when we say R is equal to 2 and R is equal to 4. So this recursive process, right, we start with an input X, and that let's go here. We start with an input X. And this the input to the block is like it's in the BSD shape, right, and it's typically from the previous block or embeddings. Then we have the first forward pass from the section 3.3, which we took over. That is the attention, then the blending, the FFN, and the cache update, right? So that is achieved. So feed forward processing is done. Now the next step, which is recursive iteration. So for I is equal to 2 till R, right, it's doing that. So instead this recursion which we have over here, instead of passing the output right away to the out block, we are thinking now. So the out which is being passed to the next block, now that becomes an input, that is a new input X. So the out which we are getting from section 3.3 is now being assigned as X, and this is going to be used for the next iteration within the same block. So if you want to represent it, it's something like X of I is equal to out of I minus 1, something like this. And then we repeat the forward pass, which H of I and everything. And after R iterations are done, whatever R is, the R count, we pass out of R. We pass this out to the next block. So the keywords over here, there is the recursion, obviously, then there is the attention processing, basically with the KV cache, it's static, but the input evolves. There's the state blending, FFN, per token, block level, all that stuff, right? So it's iterative refinement. Basically, the first pass is done, which uses the KV cache context. Then the subsequent passes which happen, that is the state refining itself and adjusting based on the previous iterations which are there. This is able to smoothen out any sort of like inconsistencies or any sort of patterns. It's able to reinforce those patterns. So basically reasoning steps. And then obviously there's the role of alpha, which basically it tells the favoring of it, and the effect of R, which is more iterations mean deeper refinement. And for, let's say, for more complex tasks, R can be set to 4, and for simpler tasks, then R is equal to 2. Now, one major problem with this is too many iterations, right? Too many iterations with a high alpha. So with high alpha, we'll just write it as A, but we know it's alpha, could lead to something called attractor states. Attractor states. So that's a keyword for this section as well. Oops, 1 second. Attractor states. Now, some people might have heard of this, obviously, and some people might not. It is normal to not, obviously. And it's, to be honest, I'm pretty sure you could understand what this could possibly mean just from simple English understanding. But attractor states basically is repetitive loops. That is, in early tests which were there in the paper, it was being stuck in these loops forever. We don't want that. And that is the reason for including alpha and R to control it. Control is still required. Even for recursion, control is still required. So finally, we'll come to the comparison which we have been doing for the every other section. Comparing it with Llama and SST over here. Llama and SST. Right. So the passes per token for Llama. One is passes per token. For Llama, it is one forward pass, 1 FP per block, which is there. For SST, it's R recursive passes per block, which is there. State evolution, which we know, Llama discards it. State evolution, SE, it's a dustbin basically. And for SST, it's iterative refinement via recursion. So this recursion is improving basically. And another point which I have in my notes is cache usage. So for Llama is KV cache, and for SST is KV cache plus the latent state cache which is there. So what is this doing now? So let's go a bit towards the data, right? Let's try to understand what is this reasoning actually helping us do. So if we go towards the data, let me just search for it. Yeah, over here they're talking about 89.01 accuracy. Basically, recursion is allowing SST to think harder, if quote unquote think harder about each singular token which is there. So that improves performance in GSM 8K, and it gives out an output of 89.01% compared to, I believe it's according to my notes, it's 84.5 for Llama. Even metacognition, that is multiple passes, it would allow the model to reflect on its state, and that can be seen in some introspective aspects. So something like, I think I remember something, yeah, right? Or do I something? This is these are self loops which are happening. 1.3 state stream strength. So alpha was set to 1.3% over here, and so you can see this correlation between introspective language and pattern disruption, which our earlier experiments sought to investigate, is clearly demonstrated in this sequence. I feel a sense of wonder. No, that's not it. Here, the stuttering patterns emerges precisely during attempted self-description aligning with our metacognitive evidence framework. So, like the word, like the keyword, introspection, right? It's the reasoning is allowing it to do that, and the compute cost which is there, R is multiplied with the block computation. So R is equal to 4, so that 4 is quadrupling the flops per token. So that's a trade-off for better performance also. So finally, for each section, we have been visualizing stuff as well. So we will explain it here only in this one. We will take this color, and yeah, okay. So what is the first pass? The first pass which is there. Think of this as let's think about this. First pass you could, which is H basically. That is your any sort of figurine. Let's say any sort of figurine which we have. It's a rough framework. It's rough. It's not worked upon that well. It's basics, right? It's like you can think of it like boilerplate code, and it's mixed in with some functions which you have written. This is figurine, right? So it has some amenities. It has like a hat. It has like boots and everything. This is your H blend. These accessories which it has is H blend. HBL I'll write it as, and this is shaping out to a out, right? So this final figurine which is there with a hat and boot, this is out. Now, before we send it away, we are going to recurse, right? So we're going to start adding some new features, maybe some eyes, maybe a smiley face, maybe polish the whole figurine itself. Like it is rough, right? So we need to maybe smoothen it out or something like that, chisel it, something. And we do it on the same figure R times. And we are refining the details which were not done in the previous one. And alpha is basically in this figurine is how much of improvement is happening. So what improvement is happening and how much of it is happening is being controlled by alpha. So this is this section. This is 3.4. Now we will focus on 3.5 section, which is processing cascade, right? So we'll tackle this now. Processing cascade is the next section which we're going to talk about, and that is basically describing how SST, that is state string transformer, is processing a single token through its entire stack of transformer block, sorry. Where it is integrating, its persistent layer, and it's doing recursion and everything. It's doing all of that, right? So we need to talk about that now in section 3.6. So let's come here. Okay. So like I mentioned, in traditional transformers, each block performs a single computation. So in traditional transformer, one computation, one comp. Whereas in SST, this is so the SST cascade which we have over here, SST cas, which we have over here, is multiple attention, state blending, and recursive state across all the blocks which we have. So what does this do? This creates a layered steps, right? Layered with iterative functions. Like all these layers are going through refinement processes before each token and protecting. So we have to unravel all of this step by step in this. The three main functionalities are token space flow, internal temporal flow, and internal vertical recursion. Those are the three keywords which we are focusing on, right? So what is it doing? The cascade in this case is the you could say it's the end-to-end flow of the computation which is happening for a single token through the stack of SST's transformer block, which is over here. The end-to-end computation of a single token is being worked upon in this transformer block. So there are 32 blocks in Llama 3.1, that is the 8 billion parameter, and each block applies a forward pass, recursion, and it updates its own latent state cache before passing its output to the next block, right? The key difference is in Llama the cascade is straightforward. In SST, each block's computation, like I mentioned, is recursive in nature, so it's repeated R times. So let's try to understand this step by step, right? So we have the input tensor over here. We have the input tensor, which is x of 0, let's say, and it has the shape that is BSD. So batch size we can take 1, S is the sequence length, that is the tokens which is processed so far, and D is the hidden dimension. Now for the first block which we have x of 0, this is usually token embeddings, right? Token embeddings with rope. Token embeddings with rope. For that current sequence. Now block level processing, which we are doing. Right, in this section we were doing block level processing. So in each block, let's take that as I, right? So I is equal to 1, 2, 3. It goes all the way till let's say n, and n is the total number of blocks. So we have a recursive loop for each specific block where I is equal to 1. I realized I should not take it as this. So small I is equal to 1 all the way till R, which we have, and it does a recursion loop of attention, state blending, feed forward, cache update, then the next recursion, right? So that would be defined the same formulas which we have with the attention. So the capital I over here and then I over here, we should have taken this as L in my opinion, but okay, we have written it as I. So all the variables which we have are going to get replaced by this this recursion loop which we have, the block level processing, right? So all the variables will have these i's and i's. Now passing through the stack, the output which is there, that is I of output which we get with I over here, and R, right? That is the recursive loop R over here. This feeds into the block, so this goes to I plus 1 now. So this becomes I plus 1. So it becomes x of 0. It was x of 0, right? Now this becomes x of I plus 1. I should have definitely taken this as L. It would have been much easier, but okay. And this continues until this is reaching its final block, let's say as pi. Okay, I just wanted to take a simple. So until it reaches this final block, which is pi, sorry. And then there is the token prediction. Then there's the next token which happens, right? Now we have the token space flow and internal temporal flow and the internal vertical recursion which we have. So let's try to understand these keywords as well, but before that we need to understand some more things. So let's try to do that. Sorry. So what we have is dynamics. So for each specific layer which we have, some earlier blocks will focus on lower level features. So something like syntax, if you're talking about code, right? And their caches will evolve based on the token relationships. Then higher level blocks like I of 10, let's say, that will be focusing on higher level reasoning. So it's building on the refined states which are already there, but it's ensuring that the cascade is ensuring that there is continuity across these levels. So let's say L is equal to 32, right? Or I is equal to 32 in our case. I is equal to 32 and R is equal to 4. So recursion is happening 4 quadruple times and I is equal to 32. So a single token which is there, it goes through 32 into 4, which is it's 128 forward passes which it will go through. That is including attention and FFN before prediction, and each goes through state blending. This obviously multiplies the computation which is there, and it multiplies it a lot, but the processing which we have obviously deepens, right? And then there is the state continuity, obviously. So the latent state cache allows it to maintain a memory, like we keep talking about, right? So let's visualize this, then we'll talk about the keywords. In terms of the difference, it's essentially the same difference which I have in my notes as the previous section. Just you got to replace the depth of the compute, where for Llama it's L passes per token, and for the depth for SST is L into R, where R is the recursion, right? So we have to visualize. Now we have to visualize this cascade which we have. So let's take example of a waterfall. We have a waterfall, right? So the water which we have over here, the water which we have, that can be represented by x of 0. This waterfall has L tiers. Okay, we've shifted to L now. So basically blocks, these are blocks basically. I'll write BL, but these mean blocks. And each tier which is there, each tier in the sense, each block which is there, swirls the water, so it swirls it. So this recursion is happening inside the waterfall, right? Mixing in like some retained water which is there, that is your cache, and it's basically doing a recursion before spilling onto the next tier which is there, because waterfalls have tiers, right? Like this it goes, it's not just one whole big slope like this. So before it goes here, it will probably do like some, self loops, then it will fall to this tier, tier 2, again like this, then tier 3, something like that. Yeah. By the bottom, when we get to the bottom, like over here, the water will be like very mixed, and it will be like, thorough, with like all sort of minerals and sediments and everything, and it will be very refined. And this mixed water, it can be used to produce a droplet or like any sort of water source. So this is how the processing cascade works. Now we have the keywords which I have to clarify. The keywords, I copied them, so I'll just, oops, not that. Oh, it was that. Okay, sorry. First is token space flow. Second is internal temporal flow. And then third is internal vertical recursion. Right, so we'll tackle all these keywords one by one. So the first keyword which is there, that is the token space flow, which is basically autoregressive token sequence generation, including the KV cache. So like we discussed before, there's the autoregressive token sequence generation, and then there is the KV cache, and all of that. So what this basically is doing is, this token space flow essentially tells us, this token space flow essentially tells us that it tells us the standard way how the information is like flowing through the whole typical transformer during the text generation. Basically the what you can say, it's the baseline flow that SST builds on. The token space flow is that, the baseline flow. So why is this important? It's because especially the KV cache, it's important. It stores the key vector and the value vector, right? And this is important because it basically is taking into account the previous tokens which are there. So token space flow, the standard sequencing which is there. Then there is the internal temporal flow. Basically this describes the new flow which we have mentioned, or which we are talking about, right? The way these arrow keys work is a bit bad, but okay. Oh, great. Okay. So this is the novel way. Novel way in the sense, this is being introduced by SST. So this is the, you could say this is the continuous evolution which we have, right? Within the, this is the continuous evolution of the latent state which we have within each FFN. Within each FFN, the continuous evolution. So the computational state space, that is the number of possible spaces which can be present within each layer of FFN, and then the continuous evolution. So let's say if the prompt was something like the cat sat on the, something like that, okay, that's the example which I've taken. The prompt is something like the cat sat on the, as each new token is processed, that is the cat sat on the, all these are tokens, right? And it's the latent state within each feedforward network, it's continuously being updated, and it's blending with the new, it's blending with the previous states which is there with the new input. So this creates a sort of like continuous trajectory which we have of memory being updated even during the KV population which we have, that is the key value cache. The latent states are continuously evolving, right? So the internal temporal flow is basically, it's a continuous time dependent evolution, which I would say, and it's driven by the weighted decay sliding window mechanism which we mentioned at the start, right? So this is what is creating the persistent memory which I kept mentioning, persistent memory within each layer which is there. Then there is the internal vertical recursion, which basically tells us how information flows between the layers of SST. That is the cascade part which we talked about, right? So these three things, the baseline and the way the persistent memory is being done, which is the section 3.3 and 3.4 part, and then the cascade, which is 3.5. This whole architecture is how SST is basically working. Now the next section is implementation details, right? Now I feel this video has already gone for too long and this has been highly theoretical. So in the next video I'll go deeper into this and the further sections which are there. Basically try to explain this in very brief manner, because they are all text based, they are written in text, so they would not take a lot of time to explain. So in the next video, implementation and explanation of the fourth and fifth section which is there. And yeah, hopefully you enjoyed this explanation. I understand this is a very it's a pretty advanced topic. You need good knowledge of past papers, like I mentioned. If you want, I can get that back again over here. These are the papers which we talked about. So I would highly recommend reading the Llama paper, and attention is all you need to understand how transformers work and how Llama's architecture basically works, because this is built upon Llama's architecture, right? So if you're able to understand these three papers, then if you read these two papers, then it would be highly helpful to understand how SST is working. All these keywords which we had for majority of the sections, like the KV cache, latent state, and then for this we had weighted decay sliding window, all of that. These seem highly technical, but when you think about them in basic, if you try to visualize them like I tried to do with each example, if you try to visualize them, they're not that hard. And that's what I truly feel ML should be, like complex topics which are there. If you're able to visualize them, then you would be able to understand even the toughest of the toughest topics. Whatever the topic may be, if you're able to visualize, then you'll be good at it. And with that, thank you for watching, and hopefully you enjoyed the explanation of the architecture. I'll be posting this soon, yeah, obviously, because I'm recording it. And yeah, thank you for watching. Take care and bye bye, and keep building and be awesome.